then you need more like gamma terms in order to get the same relative accuracy. And in fact, the variational characterization of the eigenvalues of the operator f star f give you a sense in which the eigenfunctions of f gamma are an optimal mechanism for representing band-limited functions. Okay, so hopefully I've convinced you that these functions might be interesting and worth computing. It seems worthwhile to give them a name. I'm going to note the nth eigen function by Ps sub n, and I'm indexing starting at n is equal to 0, and I'm going to use lambda sub n for the nth eigenvalue. And here are some plots of these functions. It's good to get some idea of what they look like. So
could you give us in analytic form? Is it some exponential of some kind, or what?
well, what do you mean?
So in closed form, to express this is the eigenvalue, we can write it as e to the z or whatever.
There's no good closed form for it.
Okay, no, okay.
Yeah. There are asymptotic expansions. They're mostly inaccurate. Yeah. So we're going to have to compute everything. That's part of the talk. Everything involving spheroid wave functions, we're going to have to compute numerically because the existing asymptotic expansions really aren't very accurate. Right. Here are some plots of the functions. In all of these cases, gamma is equal to 20, so the band limit is 20, and we have functions. This is, I think, the case where n is 1, n is 5 is in the middle, and n is 10 is in the right. So you have some idea of what these things look like. All right, so it's very tempting to try and calculate these functions by discretizing the integral operator f sub gamma. So for instance, one could pick an orthonormal basis in L2, take a series of Galois-Yorkin discretizations of the operator f sub gamma, and try and solve an eigenproblem for those matrices. Okay? And this is perfectly fine if what you want is to compute the eigenvalues. You cannot compute the eigenfunctions that way. So the condition number of the problem of computing eigenfunctions depends on the gap between eigenvalues. And the gaps between eigenvalues are small here.
And so you're considering function on an interval, is that correct?
That's correct, yes.
So the Fourier operator acting on functions, and there's no boundary conditions. I mean, the examples you drew seem to be functional of the whole line.
Well, they certainly extend to the whole line, but we're viewing them as defined on -1, 1.
Okay.
Right? And we have an operator. This is in some sense why we sort of we started by talking about band-limited functions on negative gamma to gamma, and we pulled back to look at -1 to 1, just so that this operator was acted L2 -1, 1 to L2 -1, 1.
So in the picture you showed, we should only be thinking from -1 to 1. Is that?
Yes, that is correct. Yeah, yeah.
Wait, the limits are -1 to 1 and those discrete things, right?
That's correct. Everything here is on the interval -1 to 1.
So in the discretization, that's what you're right? In the discretization also you just
Everything would be -1 to 1. Yeah, absolutely. Right. Uh-huh.
Does it follow that if these things satisfy some natural differential equation?
Oh, that's what. Yes. Yeah, that's the next slide.
Oh, sorry.
Yeah. No, it's fine. Right. But the point I wanted to make here is just that the nature of the spectrum of f sub gamma means that you cannot solve the problem. The problem of computing the eigenfunctions of f sub gamma is numerically ill-conditioned. It is essentially numerically intractable when gamma is not small. But luckily, these functions are also the solutions of a singular self-adjoining Sturm-Liouville problem. This is the problem. It's up here on the board. This is an old observation, right? And we will denote the Sturm-Liouville eigenvalue corresponding to the nth eigenfunction by chi sub n. And now, this is a well-behaved problem, because here I have a plot on the right of the chi sub n's, and these things are increasing and well separated. So there's no difficulty here. This is numerically well conditioned solving this Sturm-Liouville problem. And the standard algorithm for solving it, I like to refer to it as the Azotov-Shao-Rochlin algorithm, because although there's a lot of papers that published elements of this algorithm over the years, I think Rochlin and his collaborators were the first people to give a correct, complete description of a numerically stable version of it. And the standard approach works by saying, okay, we will discretize this problem by representing the function of interest, the function Ps sub n, as a Legendre expansion. We use expansions in even polynomials when n is even, and we use odd polynomials when n is odd. So we know that when n is odd, the function is going to be odd. When n is even, it's going to be even. And why we use the Legendre functions is to enforce the Sturm-Liouville boundary conditions. So the Legendre polynomials are the solution of a related Sturm-Liouville problem, right? And here we have the same boundary conditions, but a different differential operator. The differential operator is missing parameter gamma and set to 0. So we can actually think of these as the functions of band limit 0 if we wanted to. And the point is that if we expand a function in L2 in terms of the Legendre basis, well, if it satisfies the boundary condition, then the coefficients will decay rapidly. If it doesn't, we can still get such an expansion, but the coefficients decay much more slowly. And we exploit this in the following way. We take the Legendre expansion and we insert it into the differential equation. And we get a set of three-term recurrence relations for the coefficients. We can organize this as an equation that looks like this with a symmetric tridiagonal matrix. And what we do is we truncate this matrix and then solve an eigenproblem for the truncated matrix. And we only get solutions of the differential equation that satisfy the correct boundary conditions because it's only in the case of the solutions that satisfy the boundary conditions that the coefficients decay rapidly enough for them to satisfy the truncated problem. Okay? If you have a solution of the differential equation that's in L2, but it doesn't satisfy the boundary conditions, the coefficients don't decay fast enough for the truncated problem to see it.
Can I ask a question?
Uh-huh.
Before you drew the solution outside the interval of interest, I'm wondering if what you were actually drawing were the solutions of this, even outside the...
These are all in the interval -1 to 1.
Oh, I see.
Yeah.
Okay, fine.
Yeah. All right. I mean, you're completely correct that they extend their entire functions, as a matter of fact. So
The solutions to this.
yeah.
Okay.
Their entire functions, as a matter of fact. But we're just viewing them as on -1 to 1 for the time being.
This formulation is, this formulation doesn't involve it. So this condition doesn't see that it's defined from -1 to 1. So so basically what I'm trying to say is that we are effectively expanding the extended Perl-X functions onto the real line. So is our basis a good choice?
I mean, in some sense, that is correct. I mean, these are entire functions, as are the Legendre polynomials. But actually, the coefficients you get from this also represent other Perl-A functions that we're not interested in, other sphere wave functions. For instance, if you take an expansion of the Legendre functions of the second kind with the same coefficients, you get another solution that, say, lives outside of the, lives on the cut plane, on the complex plane with some cut in it, if you like, right? So, I'm not sure if that answers your question, but in some sense, the procedure you get here is not tied to the interval -1 to 1. It's more about the representation of sphere wave functions in terms of Legendre expansions. Okay? And you can look at different regions and build expansions with different Legendre functions, actually, right? So, okay. There are also almost the coefficients of representations of the sphere wave equations in terms of spherical Bessel functions, too. Okay, so, did that answer the question enough? Okay. All right, so this is sort of the state-of-the-art algorithm. The running time of this algorithm obviously depends on the dimension of this matrix that you have to solve an eigenproblem for. Here are some plots of the minimum dimensions you need as a function of the parameters gamma and n. And the behavior of the dimensions of the matrix is actually fairly complicated for small values of the parameters, but it's reasonable to think about the running time as being n plus square root of gamma n, because that is what it does asymptotically. That is the asymptotic behavior for large values of the parameters. Okay? This is, as I said, the state-of-the-art method. And I'm very fond of this method. I think it's kind of elegant how it enforces the Sturm-Liouville boundary conditions, but we can actually do a bit better than this. So, or quite a bit better, actually. So, many second-order linear ordinary differential equations admit solutions whose logarithms could be represented much more efficiently by polynomial expansions than the solutions themselves. This is more or less the observation that underlies the WKB method. In the WKB method, you exploit this observation in order to build asymptotic expansions of the solutions of second-order differential equations. What we're going to do is exploit it in a rather more direct fashion. We're going to solve an auxiliary differential equation satisfied by the logarithms of the solutions of the reduced spheroidal wave equation. And I'm sorry, I don't think I told you this, but I'm calling this the reduced spheroidal wave equation, this differential equation. And the reason is that normally when you say spheroidal wave equation, you mean a differential equation that has an extra term involving another parameter. Here the parameter is 0, and it's reduced spheroidal wave equation. All right. And what we're going to do is we're going to solve an auxiliary differential equation satisfied by the logarithms of the solutions of the reduced spheroidal wave equation. We're going to do that to build an efficient polynomial expansion of the logarithm, and we can use the logarithm to evaluate the solution that we're interested in of the equation itself. Okay? And here I have two plots up on the screen. On the left is a plot of PSN when n is equal to 100 and gamma is equal to 500. On the right is the imaginary part of a logarithm of a solution of exactly the same equation. Right? And I can use this logarithm over on the right to evaluate this function over on the left, and I probably don't need to tell you which one of these things I can represent more efficiently with the polynomial expansion. Okay? So that's the strategy. Before I explain the details of the algorithm, I need some simple technical observations, and then I need to tell you which solutions of the reduced spheroidal wave equation have well-behaved logarithms. So let me start with the technical details, and like I said, they're quite straightforward. If we have a solution y of the differential equation y prime prime plus qy equals 0 of the form e to the r, then r satisfies this Riccati equation. It might look like I'm restricting attention to a very special class of equations, but I think everybody knows that I can very easily transform essentially any second-order linear ordinary differential equation into this form, and I can certainly transform the reduced spheroidal wave equation into this form. So I'm not really making much restriction at all here. So it's easy to see that if q is real valued, then r winds up being the special form. It winds up being in the form I psi minus 1/2 log psi prime with psi real. Okay? Among other things, that means that we have a pair of solutions, sine psi over square root of psi prime, and cosine psi over square root of psi prime. And it also means that we probably shouldn't bother actually representing the function r itself. This is a complex valued function, and there's really not much to be gained by representing r instead of just representing psi. So for the most part, what we're going to do is calculate and store psi. It's a bit more efficient because it's real valued, and r is complex valued. We call psi a phase function for the differential equation. We're also interested in the associated modulus function. So the modulus function is the reciprocal of the derivative of the phase function, and this is also equal to the sum of squares of the two solutions u and v involving sine and cosine we had on the previous slide. Okay? And it can be verified quite easily that modulus functions satisfy this third-order linear ordinary differential equation, which is usually called a Pell's differential equation. So Pell wrote a paper on it in about 1897-ish. Okay? And what's nice about modulus functions is that it's usually easier to state and prove properties involving them than it is the phase functions and the logarithms. They tend to have slightly simpler structures. And so usually what you do if you want to show that an equation has a well-behaved logarithm or a well-behaved phase function is you prove something about the modulus function. And these three functions are essentially interchangeable. If you give me a modulus function, I can very easily build a phase function or a logarithm and so on, etc., vice versa. Okay, and I need one more little technical observation, which is the way we usually specify a phase function is via a pair of real-valued solutions of the equation. Okay? So if we have a pair of u and v of real-valued solutions whose Wronskian is 1, then it turns out that m equals u squared plus v squared is a modulus function, and its reciprocal is the derivative of the phase function. And this doesn't determine a unique phase function, but it determines a phase function up to an integral multiple of 2 pi, or a constant additive constant, which is an integral multiple of 2 pi. Okay, and that's usually good enough for us. We'll typically, the way we're going to define a phase function later is to take two solutions and say I want the phase function associated with these two solutions. All right, so that's all of the very simple technical details we're going to need. The second thing we need is we need to know which solution of the spheroidal wave equation has well-behaved logarithms. Well, I think this slide kind of gives the game away because I'm defining a solution of the spheroidal wave equation. This is usually called the radial spheroidal wave equation of the third kind. And it can be defined with this integral formula. This is more or less the Fourier transform over the interval 1 to infinity of the function Psn, with the small difference that we have a factor of gamma, the band limit, here in the exponential. Okay? And we can almost immediately build an asymptotic formula from this integral definition, or this integral formula defining S3. We can see that at infinity it's going to behave like e to the I gamma z over square root of gamma z. And by the way, I chose the normalizing constant for a specific reason that I'll describe later. It might look a little odd, but... All right, so it's just from this asymptotic formula, I strongly suspect that S3 is going to have a logarithm that's non-oscillatory, right? And a modulus function that's non-oscillatory and well-behaved. And why is that? Well, it behaves that way at infinity, right? It has a well-behaved logarithm and a well-behaved modulus function at infinity. And then what could cause a regime change if you move from infinity towards zero? Knowing what we know about the solution to differential equations, how could something bad happen to make this thing suddenly start oscillating as z becomes small? Okay, well that's sort of a heuristic argument that says this should probably be it. Here's another argument that I like, more heuristic evidence, and then I'll state some conjectures later that I haven't gotten around to proving yet about the particular properties of this function, but we'll get there. It turns out that Ps sub n is an L2 of L1 to infinity. And this actually isn't hard to see. You can see this because all of the spheroidal wave functions have behavior at infinity that makes them decay fast enough to be an L2, and then it's regular at the point 1. So it turns out that PS is an L2, and one implication of that is that S3 is in a Hardy space of functions analytic on the upper half of the complex plane, whose boundary values are square integrable. And one implication of that is that, there are a number of implications of that, but generally speaking, when you have a solution of a second order linear ordinary differential equation that has this property, its modulus function is going to be well behaved. Okay, its modulus function is going to be a non-oscillatory thing.
What's an intuitive way of understanding that it's in the Hardy space? I mean, is there something like?
Oh, it's essentially okay. One definition of the Hardy space is the Fourier transform of something on the interval 0 to infinity that's in L2.
So yeah, it's kind of
Yeah. So, by the way, other Hardy spaces work for this.
I mean, maybe it just doesn't grow that fast at infinity, and that's. But in the complex direction is bounded.
Right, because what happens is you look in what happens is you go up in the complex plane to the exponential function, and then you have some kind of bound on PS, right? And incidentally, this observation, it's not unique to the Hardy space with involving square integrable functions. You can weaken that quite a bit. Interestingly enough, you cannot weaken it as far as tempered distributions, which is unfortunate because a lot of differential equations have solutions as Fourier transforms are tempered distributions. So okay, but if you have one of these HP Hardy spaces, there should be no problem. All right, and why do we suspect that if we have a solution in a Hardy space of a second order ordinary differential equation, that we're going to have a well-behaved modulus function? Well, I'm going to look at a simple model. The reduced spheroidal wave equation has kind of a complicated coefficient, and you can change it into a simpler form with the change of variables, and you can do various machinations on it. But let's just imagine that we have an equation that looks like g prime prime plus k squared qg equals 0, and I hope I can at least convince you that this is a plausible statement. And here I'm going to assume that k is fairly big, and q is a smooth function that's maybe relatively small magnitude. Maybe its magnitude is roughly 1. Okay? What do I expect the Fourier transform of g to look like? Well, the Fourier transform of q as a constant is going to be two delta functions, one at plus k and one at minus k. And what happens if I have a smooth q is that it basically modulates the Fourier transform. I get something that looks sort of like a bump function around minus k and sort of like a bump function around plus k. Right? And now what happens if I look at the Fourier transform of the modulus function? Well, the Fourier transform of the modulus function looks like a slightly modified convolution of the Fourier transform of the function with itself. I have a t plus s here instead of a t minus s. And if I do that with a function that has two bumps at plus and minus k like this, well, I get the Fourier transform of a function that's clearly oscillatory, right? I'm going to have a bump at minus k, a bump at plus k, and this absolute value g squared is going to be oscillatory. But what happens if I have something that's in a Hardy space so that its Fourier transform is supported on 1/2 of the real axis? Well, now when I take the convolution, I'm just going to get a bump centered at 0. Okay, and so I get a non-oscillatory object. So if you have something that lives in a Hardy space and satisfies a second order differential equation, it's a very strong suspect, right? You suspect very strongly that its modulus function is probably not oscillatory. You can construct counterexamples of this, right? You can do strange things. But this is more or less going to be, this is a reasonable guiding principle. Okay, and let me make some conjectures that I haven't gotten. I've proved parts of these, but I haven't proved all of them, so I'll just state them as conjectures. But here are conjectures about the exact nature of the modulus function associated with S3. And let me just be clear, I don't think I said this, but I'm defining the function mn to be the absolute value of S3 squared. Again, we're looking on the real axis where the coefficients of the differential equation are real valued. So this is the sum of squares of the real and imaginary part of S3, which are separately solutions of the differential equation. So this is the sum of squares of two solutions. So this is a modulus function. And the conjecture is that, well, for reasonable values of the parameters, this modulus function is absolutely monotone on the interval 0 to 1. And that means that all of its derivatives are positive. And it is completely monotone on the interval 1 to infinity. That means its derivatives alternate in signs. And both of these are extremely strong monotonicity properties, right? If you have a completely or absolutely monotone function, that's an awfully smooth function. Here are plots of these functions. On the left is a plot of mn, and I forget the values of the parameters, but there's something reasonable. They're not trying to trick you. There's some, gamma is probably 100 or something like that. And on the right, the plot on the left is over the interval 0 to 1, and on the right is a plot over the interval 1 to 2. So hopefully, we agree that, at least if you believe these conjectures, we have a modulus function for the reduced spirited wave equation that is extremely well behaved. Okay? And I have a second conjecture here whose role is less obvious, but you'll see in a minute why I'm interested in it. And this says that if we look at S3 on the imaginary axis, we'll get a function that's n plus 2 times monotone. Okay, so it's not quite as smooth, but it's still a nice smooth function. And that means that the first n plus 2 derivatives alternate in signs. So the function's positive, its derivative is negative, the second derivative is positive, and so on. Okay? And by the way, this is, just to be clear, this is extremely different from the behavior of most solutions of the spirited wave equation, right? These are, the solutions of this equation are objects that oscillate on most of the real axis, right? They have regions where they're exponentially growing or shrinking, but they're generally speaking oscillatory functions. So if you take an absolute value, a squared of an arbitrary solution, this is most assuredly not going to happen. Okay? All right. So I need to define the phase function associated with S3, and it turns out I cheated you slightly. I've been slightly mean to you. And the way I've been mean to you is that when I defined phase and modulus functions, I did so in terms of a particular form of differential equation. And well, now I'm talking about the reduced spirited wave equation, which is not of that form. And I need to transform it into that form. And that's simple to do. If I have a solution y of the spirited wave equation and I scale it by square root of 1 minus c squared, I get an equation of this, it satisfies this equation, which I call the normal form of the reduced spirited wave equation. And it turns out we need to scale this function m I defined by 1 over z squared to get a modulus function for this. All right? And then we can define a phase function as the integral of, if this is a modulus function, then its reciprocal is the derivative of the phase function. So we'll define a phase function as an integral involving the reciprocal of this modulus function. Now, I chose the constant of integration for a particular reason. I chose it so the function sine of my phase function psi divided by the derivative of psi turns out to be regular at the point 1. And I did that because the solution I'm interested in, PS of n, is also regular at the point 1. And so this tells me that PS is a multiple of the sine, right? An arbitrary solution would be a linear combination of a sine and a cosine. But because of my choice of integrating constant, I get just a multiple of sine. All right? So how do we construct this phase function numerically? So we believe if gamma is 1,000,000, then our solutions of the reduced spirited wave equation are going to oscillate very rapidly, but our modulus and phase function should be nice, well-behaved functions. So let's compute those instead of computing the instead of building a polynomial expansion of the solutions of the reduced spirited wave equation. Let's build a polynomial expansion of the modulus function, the phase function, the logarithm, whatever, however you want to think about it. And how are we going to do that? Well, we're going to exploit the fact that we know the asymptotic behavior of S3 at infinity. And the asymptotic behavior of S3 at infinity tells us what the logarithmic derivative of S3 does at infinity. And we're going to solve a Riccati equation satisfied by the logarithmic derivative of S3 going down the imaginary axis from some very large point, some point that's very distant from 0, where the asymptotic estimate is accurate. And by doing that, what's going to happen is we're going to figure out what the logarithmic derivative is at 0. And then we can compute the derivatives of the phase function, we can compute the derivatives of the modulus function, the value of the modulus functions and its derivatives, and anything else basically that we want from that. And once we have those values, we'll solve another differential equation going forward, and it seems easiest to solve the Pell's equation to construct the modulus function. We could also solve a different differential equation to construct the phase function, or we could solve the Riccati equation going forward to construct the logarithm, but it turns out numerically it seems easiest to construct the modulus function. And so that's what we do. We solve the Pell's differential equation forward to construct the modulus function on the interval 0 to 1. And we now have the derivative of the phase function, and we need to build the phase function itself, so we integrate backwards. We know what the phase function should be at 1, so we take a point extremely close to 1. We can't use 1 because it's a singular point of the equation. And then we integrate going backwards from 1 to 0 to build the phase function itself. Okay, so how well does all this work? Here are some plots of the number of Chebyshev coefficients you need to represent the phase function as a function of gamma on the left and as a function of a parameter I call sigma on the right. I'm actually going to define sigma later in the talk, but you can think of it for now as being the ratio of n to gamma. So the behavior of the spheroid wave equation, spheroid wave functions, their qualitative behavior, doesn't really depend on the absolute value of n. It really depends on the ratio of n to gamma. You know, if n is 1/2 of gamma, the behavior of the function is very similar for different values of gamma. So it makes sense to index these things using that ratio. So that's what the parameter sigma is here. And on the left, again, we have plots of the number of Chebyshev coefficients you need to represent the phase function as a function of gamma, for gamma varying between about 100 and 1,000,000. And it's always less than 800. In fact, I think it's always less than 650. And the plots are for different values of sigma. Okay? And it actually does increase slightly with gamma. This axis on the bottom, the x-axis here is on the log scale, so this is actually increasing sub-logarithmically. So the number of Chebyshev coefficients we need does increase slightly with gamma, but it's sub-logarithmic in gamma. If we look over here on the plots of the number of Chebyshev coefficients we need as a function of sigma, which is a proxy for n, we see that it's essentially bounded independent of n. And again, everything here is bounded by something like 650. So here's a plot of, and again, just to emphasize, when lambda is something like 10 to the 6, if you use the standard Rocklin algorithm, you need something on the order of 10 to the 6 coefficients to represent it. Okay? So instead of 10 to the 6 coefficients, we're using 600. All right.
Why is there that sudden drop at around sigma is 0.6?
Aha. That's where the solutions change from being, that's where the equation goes from having a turning point on the interval 0 to 1 to not having turning points. Yeah. So what happens is everything becomes purely oscillatory. So there's actually a big stupidity in this algorithm, which I'll talk about at the conclusion if I have time. But it's still not bad. All right. And it's related to turning points. So here's a plot of the time in microseconds required to construct these expansions. This is essentially the same plot because the dimension of the expansion is more or less a proxy for the time it takes. But it is nice to say that at no point do we need more than, say, 600 microseconds to construct this expansion on a laptop. We can also plot the maximum errors, and the maximum errors aren't too bad. They do increase slightly with the parameters. That isn't surprising because the condition number of evaluation of the functions we're evaluating increases with the parameters. In the same way that, say, cosine lambda x, the error in the evaluation of that generally increases with lambda, the error in the evaluation of these functions will increase with the parameters gamma and sigma as well. All right, and here's a comparison with Shell-Rocklin, and obviously we can only compare for relatively small values of gamma, because when gamma is large, Shell-Rocklin is going to be so much slower that the axis plots will be unreasonable. But this is just to give you an idea of where the break-even points are. They're not too bad. It turns out Shell-Rocklin is faster for some very small values of the parameters, but as soon as the parameters are, say, gamma's a couple hundred or sigma's 1/2, this becomes quite a bit faster. Okay, so that's the algorithm. Any questions on that one so far? All right, so there's a problem with all of this. So the problem with all of this is the algorithm I just described requires knowledge of this Sturm-Liouville eigenvalue. So this comes out, if you use Shao-Rocklin to evaluate the prolate functions, you get this for free. It turns out to be an eigenvalue of the matrix, the tridiagonal matrix that you solve an eigenproblem for. But we're not doing that. We're looking at the differential equation directly. And we need to know the value of the parameter chi that appears in the differential equation that's associated with the solution that we're interested in evaluating. And that's, of course, the Sturm-Liouville eigenvalue. And the most obvious thing to do is to say, let's use asymptotic estimates. Well, there are no really asymptotic estimates of the spirited away functions, okay? They actually suffer from what I call the multi-parameter problem, which is that as soon as you have two parameters, it's very hard to find asymptotic estimates that are accurate for large regimes of the parameters, right? There are various things you can do, but they're quite clumsy, okay? So it's very hard, at least in all the regimes we're interested in, to use asymptotic estimates to evaluate this. The standard algorithm, the numerical algorithm for computing it, is just Osipov, Shao-Rocklin, and if we do that, we haven't gained anything. So we have to come up with our own way of computing this. And being a numerical analyst, the first thing I always ask if I have something I need to compute is, can I pre-compute a piecewise polynomial expansion of it? Because maybe that will work, and even if it takes me a long time to pre-compute it, once I have such an expansion, I should be able to evaluate everything efficiently. Okay, well, let's try and do that. That's actually what we're going to do. But unfortunately, we're going to need to invent our own mechanism for analytically continuing this function chi sub n. There is a standard mechanism for analytically continuing this in the variable n, so that we have chi sub n for complex values of n, but it is not actually suitable. I'm going to start by explaining what it is, though, and explain why it's not suitable. So how do we usually index special functions? Well, I think it behooves us to look at Legendre's differential equation first. So this is a second-order linear ordinary differential equation that has a regular singularity at infinity. And among other things, that means that you have a solution of this form, z to the nu times a power series in 1 over z that's convergent in some region. And if you insert this power series expression into the differential equation, what pops out is a very simple formula relating chi and nu. Chi is nu times nu plus 1. And what we normally do is we use nu to index the Legendre functions, right? And it turns out the functions that we're interested in are, for reasons that are fairly obvious from this expansion, the functions we're interested in are the integer values of nu, which is why we use those instead of, why we use nu instead of chi. Okay, well, something similar is true for the spherical wave equation, but of course it's much more complicated because the spherical wave equation has an irregular singularity at infinity. So when we look for a solution there, we get something in the form z to the nu times a Laurent expansion. And Laurent expansion converges on some annulus, right? But the trouble is that when we insert that into the differential equation, we get a transcendental equation connecting chi and nu. And it turns out that for each value of chi, there are countable solutions, nu, and for each nu, there are countable associated values of chi. So there's no really natural way to associate chi and value of chi uniquely with nu. Now the solution that people came up to this is due to either Meissner and or Schafke, who wrote the standard monograph on spirited wave functions. This appears for the first time in German literature sometime in the 30s, I think. And their standard solution was to say, aha, you know what we'll do? We'll say that as the band limit goes to 0, we'll make chi go to what it is for Legendre's differential equation. We'll make it nu times nu plus 1. Right? Very reasonable thing to do. This does give you a definition of chi which is more or less unique. It turns out, though, that this isn't defined for half-integer values of nu, and in fact it has branch points at half-integer values of nu. And that's not good if what you want to do is build polynomial expansions of the function. Here are some plots of chi as a function of nu in the case where gamma is 2 and gamma is 10. By the way, this issue is often overlooked because as you increase the value of n here, the jumps here get smaller and smaller and smaller. So if you plot this function for large values of nu, a lot of people don't even see these jumps, right? They're sort of hidden. This still causes problems in representing the function, though, Because of course, if you have even if you have a little gap there, numerically you'll see it, and you'll get an expansion that's badly behaved. Okay? So we're not going to be able to use this standard mechanism, and by the way, nu is usually called characteristic exponent, but we're not going to be able to use this to analytically continue our function chi. We're going to have to come up with something else. Well, it turns out that phase functions give us a really good way to do this. So let's look at this formula again. So this is representing the nth eigenfunction as a multiple of sine psi, where psi is our phase function. And we know some things about this function. It's a Sturm-Liouville eigenvalue. So among other things, we know it has n zeros in the interval 0 to 1. We know that those zeros from this formula have to occur at integral multiples of pi. And we know something about PS being even or odd. So we know when n is odd, 0 is actually going to be a root of this thing. And when n is even, the derivative of this thing is going to have a root at 0. And we can combine all that to figure out that the value of the phase function at 0 is going to be minus pi over 2 n plus 1. Okay, so the value of the phase function is a simple function of the number of zeros. Now, for Legendre's differential equation, you can just replace n with nu, and this is still true. For the spirited wave equation, obviously it's much more complicated than that. Okay? But what we're going to do is we're just going to go ahead and say, let's define a new parameter, tau, which is negative 2 over pi psi at 0 minus 1. In the case of integer values of n, this thing is a multiple of n. This is just equal to n. So we know what it is when we have one of the solutions we're interested in, right? And this quantity generalizes the notion of the number of zeros of the function ps, right? In fact, it does for complex values of the parameters, right? And we're going to go ahead and use this as an index. All we have to do is make sure that we can actually invert this, that we can write tau as a function of chi, we have to be able to write chi as a function of tau. And again, here's one of those pesky conjectures I haven't proven yet, but I claim that when you view this phase function as a function of chi, it's strictly decreasing on the interval 0 to infinity, so as chi goes up. This is, by the way, a much more interesting conjecture than the other ones. The other ones are sort of variants of things that appear in the literature. This is, I think, more interesting. I don't know exactly what related to this appears in the literature because this is sort of a sweeping generalization of the Sturm comparison theorem, right? I mean, this is a very concrete way in which a solution is becoming more oscillatory as a parameter in the differential equation increases. I'm claiming that the phase function is strictly increasing. And this is, by the way, true for a lot of differential equations. You can just experimentally see that this will be true for many, many equations of interest, okay, if you build a good phase function. And actually, for reasons that we'll see in a second, that I've kind of alluded to already, we're not going to be interested in tau. We're actually going to build a new parameter sigma, which is just tau divided by gamma. So that's not going to cause problems. We're still going to be able to use tau in order to identify the solutions that we're interested in. Okay? And here are plots of chi as a function of sigma. And so, of course, now we have these extremely nice, smooth functions instead of functions with branch points and jumps and unpleasantness. So the upshot of all this is we can just go ahead and build piecewise bivariate polynomial expansions of chi as a function of sigma and as a function of gamma, and that way we can just compute it easily, and very efficiently. And these expansions for values of the parameters gamma between 64 and 2 to the 20, which is a little bit bigger than 1,000,000, and sigma between 0 and 1.1, this takes about 0.75 megabytes of memory. Okay? And the time to evaluate this expansion and compute chi is essentially negligible. It's something like, it's less than 10 to the minus 7 seconds, something like that. Okay, so I actually had trouble timing it because the function call overhead took longer than evaluating the function. So I kept getting back a constant number, and what it was the time it took to call a function. Okay, so, all right. So how much time do I have?
Another 8 minutes.
8 minutes. Okay, so I don't know. I have some comments about further work here. First of all, it'd be nice to prove all the conjectures. I've actually been kind of waiting to see if I could get a graduate student who might be interested in doing some of this, but I might have to do it myself. But maybe the most interesting observation here is that the algorithm I just described has a running time that grows sublogarithmically in gamma. Now that's a lot better than Rockland's algorithm, which is something like O of n plus square root of gamma n. And of course, this is independent of n. But you can actually do better. You can get something that's independent of gamma. Okay? And the stupidity, which you kind of, I think, guessed a little bit, is that near the turning point, using the phase function is not a very good way to represent the function. It's great away from turning points, but near turning points, it's lousy. So what you should really do is represent the solution directly near the turning point, and then only use the phase function away from it. And if you do that, you'll get O of 1. Okay? And there's another stupidity here, which is that, well, okay, I built an expansion of chi sub, I have a little typo here, it's supposed to be chi sub sigma, and then we use the value of chi sub sigma to construct the phase function on the fly. Well, why don't we just build a trivariate piecewise polynomial expansion of the phase function itself, right? That's a little more complicated, and you have to be careful doing that to make sure that your expansion isn't huge or something, but you absolutely could do that. And then your algorithm goes from taking 10 to the minus 4 seconds to first construct the phase function and then evaluate everything to 10 to the minus 7 seconds to just evaluate the expansion, right? Okay, so that can absolutely be done. This is kind of a pipe dream. It would be really nice to have results that actually bound the number of Chebyshev coefficients you need to represent various functions here. Okay, there are actually, shockingly, you might think in numerics that there are a lot of results of that type, but there aren't. There are a lot of, say, asymptotic estimates, and there are a lot of vague heuristic statements, but there aren't a lot of concrete bounds that say, if you give me these parameters, I need 600 coefficients, right? It would be really nice to have something like that here. Okay. There's more that can be said, but I think I'll stop there.
Anyone have any other questions?
In last half of the talk, you mentioned that you'd like to compute chi. Do you think a fast algorithm that enables you to compute a single chi would be useful?
I don't really know. I mean, that's what we have. I don't really know of any use for it outside of the fact that I use that chi to compute the spirited wave functions.
So I'm thinking about using Röglin's scheme to compute, because the usual way to use the Röglin matrix to compute eigenfunction is to throw away all the trailing coefficients.
Yep.
But I think because that matrix is diagonally dominant,
Yep.
I think if you like a particular chi n, we can throw away the the coefficients in the beginning as well, so we get a trunk of the matrix in the middle. Then we can do some inverse power iterations to get that, and that matrix would be a constant size. So I guess we can use some inverse power iterations to get chi n quickly.
Yeah, I think this works. Okay, this is most likely going to work for certain values of the parameters, and then there are others where you need the full, you need a big Legendre expansion.
Yeah, but for that case, there is a paper by Rogan and Shaw that's using the Hermes function to expand it.
You could probably do that. I'm not claiming there's no other way to evaluate the chi sub n rapidly, right? I'm just claiming that this gives you one mechanism for doing it. Yeah. I think what you're proposing, though, is already starting to get complicated. You need different methods and different regimes. This scares me because when you're trying to build asymptotic estimates for these things, what happens is it's a little tricky. You could build estimates for when sigma is small and gamma is large, when sigma is large and gamma is small easily, but then when sigma and gamma are close to each other in size, things become difficult. My suspicion is if you play that game, you'll run into some case like that. It will work great in certain regimes, and then there'll be a regime where, things are difficult. But I could be wrong. I'm not suggesting that it won't work. I'm not saying for sure it won't work. I'm just a little nervous.
If there are no other questions, let's thank our speaker again.